Looking at section 11.1, finding limits using tables and graphs, we are going to understand limit notation, find limits using tables, find limits using graphs, and find one-sided limits and use them to determine if a limit exists. So if you were to go through kind of the book and look at some of the introduction stuff that they have on there, I thought this was a good example as to what happens with a limit. So it says, suppose that you and a friend are walking along the graph of the function f of x is equal to x squared minus 4 divided by an x minus 2. So if you look at the graph over here on the side, it looks as though one of the friends is walking kind of downhill and it is approaching what looks like a hole in the graph right here. And then we have this other friend who is walking up the graph, approaching that same value. And why are they approaching that too? Is because if you look at the denominator, an x minus 2, a value that would not exist in that function would be if x was equal to 2. If you remember back to a previous chapter, before we did all the trig review, we would have looked to see where our asymptotes or possible holes are in a function. So we would have taken that denominator x minus 2 and set it equal to 0 to find that x could not be equal to 2. That would give us some sort of either an asymptote or a hole in our graph. The reason why this one was a hole is if you were to take the top of that fraction and break it down, factor it down, you'd have an x plus 2 times an x minus 2. And then on the bottom, you have that x minus 2, which meant that you had that common factor. X minus 2 would cancel out, and it looks like there shouldn't be any issue with your graph. But there is an issue. There's a hole in your graph. And so what a limit is going to do is it's going to try to figure out, well, what is the value of this function at x is equal to 2? So what they do is they do limits. And what a limit does is it has, so if I go back to this little graph, the friend that's coming and kind of walking down that function is going to get as close to that value as it can without actually touching that value. And the friend that's coming from the left-hand side and going up this kind of hill is approaching 2 as much as it can from that left-hand side, but not actually going to equal 2. That's what a limit does. It gets as close as you can to that value without actually hitting that value. I think teenagers do that with their parents a lot. You push the limits. How far can I go before I'm like in serious trouble? So the book kind of goes through some of the explanation as to some of the approaches we're going to do. So today we're going to look at some from the perspective of a graph, and we're also going to look for some from the perspective of making a table. So if I were to continue down a little bit, what they did is they took that exact same function, f of x is equal to x squared minus 4, and divided it by x minus 2, and they made a table of values. They said, we know that if x is equal to 2, we have an undefined value. So what happens as we approach 2 from the left-hand side, and what happens as we approach 2 from the right-hand side? Now they want to get as close as they can without equaling 2, so they break it down really, really itty-bitty. 1.99, 1.999, 1.9999, and then they jump to the other side and they go 2.0001, 2.001, 2.01, and then they start looking at these values. What did we get as we got close to that 2 from either direction? Well, it looks like we're approaching the number 4, which we were able to see on that graph up here. We see that that is approaching the number 4, but it's not actually going to equal 4. But that's what the value is going to be as we get as close to that value as possible. Another means to do that is by going on the graphing calculators and looking from the table perspective, and then just kind of evaluating kind of what's happening from the left-hand side and the right-hand side. So that's what a limit is getting as close as you can without actually equaling that number. So limit notation and its description, it says, suppose that f is a function defined on some open interval containing the number a. The function f may or may not be defined at a. So the example we just looked at, it was not defined at that value for a, because if we divided by that number, we'd get an undefined. That's why it's not defined. So it tells us that the limit notation, the limit as x approaches a, that's what this means right here, the limit of that function as x approaches a, f of x is equal to L, whatever value we can find from it. So it says it's read as the limit of f of x as x approaches a equals the number L. This means that as x gets closer to a but remains unequal to a, the corresponding values of f of x get closer to L. So finding limits using tables, it says to find the limit as x approaches a of f of x by using a table, we evaluate f at chosen values for a. Excuse me. So we're going to approach A from the left, choosing values of x that are close to A, but still less than A. And we're going to approach A from the right, choosing values of x that are close to A, but still greater than A. So let's take a look at an example. So if they want us to find the limit as x approaches 3 of a 4x squared, well, first things first, when you look at this function, the function 4x squared, that's a quadratic. If you think about a quadratic, right, it makes a parabola. Is there any limitation to what you could put in for x? Well, there isn't a limitation. Because it's a quadratic, we know that it's going to be all real numbers, which means that we're not going to have a problem evaluating this function at that number 3. So actually, if I were to go and check it, 4 times 3 squared would give us 4 times 9, which would give us 36. We obviously are not going to have any problem evaluating this function. So we know that when x was equal to 3, we end up with 36. But we're going to show why that is true, because as I said, not all of these are going to exist at that function or at that value. So it says that we make a table of values choosing values of x close to 3. So we're going to plug in these numbers, and all you're going to do is get a handy dandy calculator and plug some numbers in. So we're taking 4 and we're multiplying it by our x value. Let's start with 2.99, and then we're going to square that. And so we end up with, we'll try to do this quickly, 35.7604. If I take 4 and I multiply by 2.999 and I square that, we end up with 35.9760. 35.9760. If we take 4 and we multiply it by 2.9999 and we square that, we end up with 35.9976. So obviously the slightly bigger that we get, right, we're only kind of adding in an extra 0.9 somewhere in there, or going from 99 hundredths to 99 thousandths to 99 10 thousandths. As we're getting a little bit closer and closer and closer to that 3, we see that it is approaching that 36. Now, if we jump to the other side of the 3 and plug in the 3 point whatevers, let's see what happens there. So if we had that 4 times 3.0001 to the second power, that gives us just on the other side of 36, right? 36.0024. 4 multiplied by 3.001 squared. That gives us a 36.0240, and 4 times 3.01 squared ends up giving us a 36.2404. We get rid of that calculator. So we can obviously tell as we are approaching from the left-hand side and as we are approaching from the right-hand side, we do end up approaching 36. So we infer that the limit as x approaches 3 of 4x squared is going to equal 36. Now, as I said, it's not always going to be that simple of, oh, I just plugged in, the number 3 for x and I got 36. There are cases that you have to make the table. You have to look at as it approaches from the left and from the right. So what happens when we look at some graphs? So it says that the limit statement, limit as x approaches a if f of x is equal to L is illustrated in the figure. So there are 3 different types of graphs we're going to evaluate. So the first one, as you can see, it goes from left to right. All along that function, there is something on that function. As x approaches a, we have a limit L. We have a filled in circle. The next one, you see that function, but then we have a hole in the function. And the third one, we have that function with the hole in the function, but they give us this extra little piece that's happening up here. So we're going to look at each of these 3 graphs individually. So the first graph, it says when we have that limit as x approaches a, if f of x is equal to L, as x approaches a, f of x approaches L. At a, the value of the function is that limit. It is that number. It's equal. It exists right there. It's shown that it's colored in. So we can say the value of the function is equal to the limit. The next one had that hole in the graph. So it says as x approaches a, f of x approaches L. So it's going along this curve and it's approaching this value of L. And it's approaching that value of L. But it's not defined at that number because it has a hole in the graph. The third one says as x approaches a, f of x approaches L. So again, going along this curve and going along this curve, we see that it is approaching that value L. But it says, notice, however, that the value of the function at a, f of a, is not equal to that limit. Why? Because there's an extra little dot up here. So the value at a gives you another value than the limit. So 3 different cases with our limits that we're going to look at. So let's take a look. It says finding a limit using a graph. So if we have the limit as x approaches -2, the limit as x approaches -2. So we find our -2 value on our graph and we go to our function. As we approach that -2, what are we approaching? We are approaching the value 5. But it asks then for what is the value of the function at -2. The value of the function at -2 is wherever we see that colored in circle. That colored in circle is at a value of 3. So the limit and the value of the function are not equal to each other. So talking about a one-sided limit, it says the left-hand limit. So we have the limit notation, limit as x approaches a, but notice there's an extra little thing in here. There's a little negative sign. That means that we're going to approach it from the left-hand side. So it's read as the limit of f of x as x approaches a from the left is equal to L and is called a left-hand limit. This means that as x gets closer to a but remains less than a, the corresponding values of f of x get closer to L. Now the right-hand limit, we have similar notation, except now we're going to have a little plus sign. So the limit of f of x as x approaches a from the right side is equal to L and is called a right-hand limit. This means that as x gets closer to a but remains greater than a, the corresponding values of f of x get closer to L. So there are equal and unequal one-sided limits. So one-sided limits can be used to show that a function has a limit as x approaches a. So it says the limit of the limit as x approaches a of f of x is equal to L if and only if, kind of all the way back to some geometry, talking about some reasoning skills, if and only if. It says if the limit as x approaches a from the left is equal to L, and as the limit as x approaches a from the right is equal to L. If they're both equal to the same value, then the limit is equal to L, whatever that number is. It says one-sided limits can be used to show that a function has no limit as x approaches a. So this one says if the limit of x approaches a from the left is equal to L, and the limit as x approaches a from the right is equal to another number. They used m. If L and m are not equal to each other, the limit does not exist. So let's try one. So it says to use the graph of the piecewise function f to find each of the following or state that the limit or function does not exist. So we want the limit as x approaches 0 from the left. So we go to wherever 0 is, and we're going from the left-hand side, which means we're going to kind of jump on this blue line that was here, and we're approaching from the left. So as we are coming along here from the left-hand side, what value are we approaching? We are approaching the y value of 2. If I look at my next one, my next piece says, as I am approaching x from the right. So if I'm going from the right, that means that I'm going from the right-hand side. I'm going to approach 0, which means that I'm kind of going along this green line here, and I'm approaching 0. That means I'm going to have a value of 1. So they want to know the limit as x approaches 0, meaning from the left and from the right. Are they the same value? Well, 2 does not equal 1, which means that our limit does not exist. If you want to put a DNE, that's fine. Does not exist. They are not the same value. There is no limit. It does not exist. And then the last piece wants to know, if you were to just have the value of the function at 0, where is it colored in? It's colored in at 1.